This video is going to talk about the topic of sets. Now, a set just means a group of items, usually alike, but they don't have to be. And a set can be a set of anything. You have a set of car keys for your different vehicles. You have a set of textbooks for the courses you're taking this fall. And of course, in math class, we're gonna be talking about sets of numbers. Now, when we are looking at a set of numbers, then we use our squiggly brackets here to indicate that we're talking about a set. And then there's two different methods that we can use to explain what's in the set. One is what's called the roster method or the list method, and that is where we can just literally list the items that are in there, the elements. Okay. So maybe I have the set of numbers 1, 2, 3. Maybe that set is really large, but still finite, meaning there's a countable number of elements in it, but maybe I don't want to list them all. So I can write 1, 2, 3, ... 100, which would indicate that, that we're talking about 1, 2, 3, 4, 5, 6, 7, and we're counting all the way up until we stop at 100. There are some sets that are infinite, which means they continue on forever. So, for example, if we started again with 1, 2, 3, and just put the ... there, and no largest element, like we did before, then that would indicate that we continue counting forever. Okay, the next element would be 4, and then 5, and then 6, but we would never stop. Again, if the set never stops, it's called an infinite set. Now, there are some sets that we encounter, like this set here, 1, 2, 3, 4, 5, 6, and so on and so forth, that we encounter often enough that they've been given names. And so the set of numbers that I have listed here is the set of natural numbers. And notice that the natural numbers start with the number 1. If we want to talk about the set of whole numbers, then all of the natural numbers are also whole numbers, 1, 2, 3, 4, 5, 6, 7. But also included in the set of whole numbers that's not a natural number is the number 0. So again, all of the natural numbers are also whole numbers, but all of the whole numbers are not natural numbers. All of them are but 0. We can continue to make this set a little bit bigger and talk about the set of integers. And when we talk about the set of integers, again, all of the whole numbers are also integers. So 0, 1, 2, 3, 4, 5. But also included in the set of integers is all of the opposites of those whole numbers. So -1 and -2 and -3 and -4 are in the set of integers. If we want to make that set even bigger, we can talk about the set of rational numbers. When we see the word rational in math class, okay, what we're going to see here at the beginning of this word is the word ratio. The rational numbers is the set of all numbers that can be written as fractions or as ratios of two integers. Now, the problem here is if I want to explain that to the reader, I can't do what I did on these 3 sets up here, meaning I can't just write 2 or 3 or 4 elements down and put a ... and then the reader would understand what was going on. I could try to make a pattern with my fractions, but then when I go ... it would be difficult for the reader to understand that I'm talking about any fraction that can be created at all. So in order to explain what's in the set of rational numbers, we're going to take a minute to talk about set builder notation. In set builder notation, we still have our squiggly brackets that indicate we're talking about a set, but there's 2 pieces now. Instead of a list with the elements separated by commas, here on the left side, there will be an expression or something that explains what our numbers look like. Then we have a vertical bar here, and the vertical bar means such that or so that. And then on the right side over here, we give an explanation about what x represents. Okay. That explanation can be in words, it can be using mathematical symbols, it can be a combination of both. So we can say, let's talk about the set of all numbers x so that x is even. Okay, my explanation here would be in words, and then if someone wanted to start making a list, they could say, well, I'm talking about 2, 4, 6, 8, 10, and so on, or 0, or -2, -4, -6. Okay, I could on this one actually make a list with my dots, and I could use either approach. Okay. Or I could say I'm talking about all of the numbers y, so that y is less than or equal to 4. So I could use symbols here instead of words to explain what this expression represents. So now going back to our fraction idea here with the rational numbers, we know a fraction has two pieces, a numerator and a denominator. And the letters we choose here aren't important. Most authors will use p over q. You could say x over y or a over b. Okay, or your favorite two letters there, one over the other. But our rational numbers look like anything looks like p over q, so that p and q are integers. P and q are integers is a piece of it, meaning I can pick any number on this list. I could put 3 over 7, I could put -2 over +9, I could put 6 over 3, okay, but I can start picking numbers from this list up here. I can put one on the top and one on the bottom. Okay, now while p can be any number from this list, if we think to what we know about fractions, q is in the denominator, and the one number I can never divide by is 0. That makes the fraction undefined. So if there's any restrictions on anything I've said right here, p and q are integers, but I have to make sure that I don't pick 0 for q. 0 for p is fine, but 0 for q is not. Oops, sorry. So set builder notation here, this would be how we would describe the rational numbers. Now anything that can be written as a fraction is considered rational. So let's change colors here for a minute. So notice any of these numbers up here are rational because the number 3 can be written as the ratio 3 over 1. Okay, or the number 0 can be written as 0 over 5. Okay. Also numbers, fractions like 1/2 or -4 over 11 or anything like that. But also the decimal value 0.7 is considered rational because if we set its real name instead of 0.7, this is the fraction 7/10. So numbers may not be given to us in fraction form, but if they can be written as a ratio of two integers, then they fall into that category of being a rational number. So again, remember that all natural numbers are also whole numbers, all whole numbers are integers, all integers are rational numbers. But instead of making that set bigger, let's talk about the set of irrational numbers next. Now, hopping to English class for a minute, if I put IR in front of a word, think about what that does to its definition. Okay, if something is irregular or irrational or irresponsible, okay, the IR negates the definition of our word or means not. Okay, so when we go to write the definition of irrational numbers, we can say just that. We can say we're talking about all of the numbers x, so that x is not rational. So understand that between the set of rational numbers and the set of irrational numbers, there is absolutely no overlap at all. Okay, a number either can be written as a fraction or it cannot. Some examples of numbers that are irrational. There are numbers that we don't use in algebra class very rarely, if ever. Numbers like pi. Okay, pi cannot be written exactly as the ratio of two integers. Okay, a lot of our roots and radicals, the square root of 2 is an irrational number. The number that we'll see to the middle, around the middle of college algebra is e, which is the natural base. We'll use that with our exponential and our logarithm functions. Okay. If you're looking at the decimal representation of any of these numbers, they not only go on forever, okay, they're non-terminating, okay, but they're also non-repeating. Okay. If I looked at the decimal value 0.3 repeating, where the 3 goes on forever, okay, it goes on forever, but there's a pattern. That's our ratio 1/3. Okay. Pi not only goes on forever, but there's no pattern to that decimal value. So once again, there's no overlap at all between these two sets. A number either can be written as a ratio of two integers or it cannot. If we take the set of all rational numbers, so any number that can be written as a fraction, and we dump it into one big pile with every number that cannot be written as a fraction, we make one big, huge set of numbers out of that. That's our set of real numbers. So we can say the set of all numbers x, or if you don't like the letter x, pick a different letter. Okay, so that x is either rational or irrational. Okay. I used to be able to say any number that comes out of your calculator is a real number, but some of the fancy calculators now, they don't even have to be all that fancy, also spit out complex numbers. Okay, so if you go to your mom or your grandma's purse and get out her old calculator, any number that comes out of that is going to be a real number. Now, as a general rule, I do not take time and spend time on tests and quizzes. I will not quiz you over, explain the difference between the rational numbers and the integers. I will not say, give me 3 examples of whole numbers that are not natural, because you can't do that. But what it is important is when we talk about things like exponents that are integer values, or maybe we're talking about rational expressions, you have to understand what is and is not in the set of integers, or what I mean by a rational value. Okay, so make sure you're kind of clear and you look at some examples in the book. You look these over and have a general understanding of what which of these words means what numbers are in which sets, because some of the numbers are in more than one set. But again, overall, I'm not going to test or quiz you over the details and the definitions of these. Okay, let me know if you have questions.